Let's look at matrix exponential solutions for transition probabilities. We have finitely many states, and we've seen this equation already. This is the matrix form for the Kolmogorov equations. Here they are. The sum here represents taking the dot product between the ith row of P and the jth column of R. And so these two equations are one and the same. The only difference is that the ones here are prescribing entry by entry. So this would be the ijth entry of this side of the matrix, and the same thing goes for the right-hand side. And I've mentioned back then that we're going to have a solution which looks like this kind of funny way of writing e to the, and it's like exponentiating a matrix. This is called a matrix exponential. I can explain what this means. But it is a way to compute any pair of probabilities and the transition between them in any finite time t. So let's look at ordinary differential equations, just in one dimension. So if you have a function p that's one dimensional, gives out real numbers for any time t. And we look at this ordinary differential equation, it's not too difficult to check that this is the solution. Take a derivative of p here, the r will come down, that explains this r here, and the exponential will stay, which explains the p of t over here. And so we've taken the derivative and we checked that this exponential form is indeed the form of the solution. And now we're going to come back to this matrix form, and the first thing to kind of wrestle with is that in here, in one dimension, multiplication of real numbers is commutative. So I could have put the r on one side or the other side, it wouldn't have mattered. In general, matrix multiplication is not commutative. So you have two matrices, you multiply them, say matrix A times matrix B, it's not the same thing as B times A. But in this case, it does turn out to be that these equations hold. And so the r can actually be put in the front or the back. And this corresponds to what are known forward or backwards Kolmogorov equations. When the r is in front, it's called the forward equation. When the r is in the back here, it's called the backward equation. And the solution to these, even though this looks like a complicated matrix, can actually be computed, and it's represented in this form. So this alone doesn't really mean anything. I have to define what this means. It's defined in terms of a matrix exponential because I'm taking the, an exponent here is a matrix. And so if I take any matrix A and I want to define e to the a, the exponent, exponentiated a, this is what it's going to look like. We're going to use a Taylor expansion formula. This is what it would look like in one dimension. So e to the x has the following Taylor series, and we're going to mirror that, and we're going to take powers of a matrix and divide it by k factorial in this whole infinite series. The first term, by the way, is the identity. So, any number raised to the 0 power is 1. Any matrix raised to the 0 power is the identity matrix. The identity matrix is the one with all ones on the diagonal and zeros elsewhere. So I've left a couple of links here to take a look. But you can see how this left-hand side is sort of a little bit mysterious, but the right-hand side is very straightforward of what to do. We know how to take the k power of a matrix. You just take it and multiply it by itself k times. You know how to compute k factorial. And so, the right-hand side is kind of ready for evaluation. It may be a little bit difficult, and for this reason there are packages that go into computing this infinite sum. But at least in principle, we know how to evaluate it. And now what we're going to do is check that that is indeed the solution. Let me backtrack a little bit. What we're going to do is try to check that these ODEs are satisfied by this matrix exponential. And this is it's not a difficult calculation. We just have to take a derivative of this matrix exponential, where instead of the matrix A, I'm going to plug in the matrix RT. T is just going to be a number multiplying a matrix. That's the same thing as taking T and multiplying every single entry of the matrix R by T. So you immediately see that by definition, e to the RT is this giant sum here, and I'm going to take the derivative right in there. to take a little bit of time to maybe justify that, but for now we're going to just go on and pass the derivative through. And that derivative is going to take the t to the k, differentiate it to bring the k downstairs and leave a k minus 1 in the exponent of t. And now that I'm here, I see that my sum here runs from 0 to infinity, but I've already brought down the k, and therefore I can run the sum from 1 to infinity. And now all I'm going to do is try to rewrite things in a way that kind of all the exponents match. First things first, I'm going to cancel the k with the k factorial to leave me with a k minus 1 factorial. And now I'm going to do what I just said, which is try to make sure that the exponents all match. So I have a k minus 1 downstairs. I have a k minus 1 in the exponent of t. I'm going to now try to create a k minus 1 in the exponent of r, which is basically just writing out what the kth power of the matrix is. If I want to take the kth power of the matrix, I just multiply it by k times, which is the same thing as taking r and multiplying it by to the k minus 1th power of r. So this step should be clear. And now I've pulled the r out in front of the sum, and I now am going to recognize the sum as the matrix exponential itself, because I'm summing from 1, which inside the k minus 1 is going to start from 0. So this reverts me back to a sum from 0 to infinity, with now the multiplier r in front, and that recovers the backward Kolmogorov equation. And the forward one would have been exactly the same, because right at this step, I didn't have to write that rk is equal to r times rk minus 1. I could have written it, so picking up right here, right, we went to this step, but it could have, or it might have as well, have been this step right here. So r to the k is also equal to rk minus 1 times r, in which case now the r is on this side, all the other operations remain the same, and you pick up this answer, which is the forward Kolmogorov equation. The final thing is the initial condition, which says when time is 0, what are the entries of this matrix? Well, there's only one way to get somewhere in time 0, that's to the same state. And so the initial condition is the identity. And so if you take this solution that we have and you want to verify that this is the initial condition, just plug in t equals 0, that's going to leave you precisely with the identity matrix. This sum goes away because it has a t. And so the initial condition holds. In the previous 2 slides, we verified that the forward and backward Kolmogorov equations holds. And this is what you're going to have to solve if you want to find out the transition probabilities between any 2 states of a finite state continuous time Markov chain. Don't do this by hand. Outside of very special cases, this is not going to be possible. Instead, if you're using Python or R package, I've left 2 different links here to compute matrix exponentials. So this is the command for computing matrix exponentials in R, and this one is the same for Python.